In this lesson, we're going to go over problem solving and data analysis for the SAT. So let's get started with ratios and proportions. What is a ratio? A ratio compares two quantities. You can write a ratio as A to B, A colon B, or as a fraction, A over B. For example, if Sarah has 4 pencils and 3 pens, what is the ratio of pencils to pens? So we're asked to compare the number of pencils to the number of pens she has. So that's going to be 4 to 3. Or we could write it as this, 4 to 3 or 4 to 3. It's the same thing. These three all mean the same thing, and that is that she has 4 pencils compared to 3 pens. What is a proportion? A proportion is simply a statement that two ratios are equal. Proportions help us scale quantities or find unknown values when one part of a ratio changes. So, in other words, given one ratio and we want to scale it up or down, we want to know what is the equivalent quantity on the other side. So let's look at an example. A painting recipe uses 2 cups of red paint for every 5 cups of white paint. If you want to use 8 cups of red paint, how much white paint is needed? So the ratio of red paint to white paint in this painting recipe is not going to change. It's always going to be 2 red to 5 white. But what if I don't want to use 2 cups of red paint? What if I want to use, like in this example, 8 cups of red paint? The question is, how much white paint should I use? Again, whatever this ratio is, it's going to be equivalent to this one. They're going to be the same. It's just that the quantities may differ, but the actual value is going to be the same. So if these are equivalent fractions, if you remember, when you multiply 2 by 4 and it becomes 8, we should also multiply the denominator by the same value in order to keep the fraction equivalent. So we should multiply the denominator by 4 as well, and we would get 20. So we know that if we use 8 red cups, then we should use 20 white cups of paint as well to keep the ratio of red to white equivalent. What is a rate? A rate compares two quantities with different units, like speed or cost per item. So for example, $10 per burger. So before we were comparing cups of red paint to cups of white paint. In this case, it's a little bit different. It's $10, which the unit is in dollars, over 1 burger. In this case, the unit is in burgers. So we're comparing quantities with 2 different units. Or we could say 50 miles per 1 hour. This is also a rate because we're comparing quantities with different units. This one has units miles, this one has units of hour. Okay, let's look at types of ratios. Let's say that we have a fruit bowl that contains 2 apples, 3 bananas, and 5 oranges. The ratio of apples to bananas is going to be 2 to 3, right? 2 apples to 3 bananas. And that's called a part-to-part ratio because apples and bananas are both a part of the entire thing. The entire thing or the entire collection of fruit is going to be 10 pieces of fruit. We have 2 apples plus 3 bananas plus 5 oranges, so the whole thing is 10 pieces of fruit. So if I were to ask what is the ratio of bananas to total fruit, that's going to be 3 bananas to 10 pieces of total fruit. And this is a part to whole relationship because bananas is a part while 10 pieces of fruit is the entire thing. That's the entire fruit bowl. The ratio of oranges to total fruit is going to be 5 to 10. This is also going to be a part to whole ratio because we're comparing the part, which is number of oranges, to the whole, which is the total number of fruit. Let's look at another example. A jar has 90 marbles. 1/3 are green. What is the ratio of green marbles to total marbles? Well, let's look at first how many green marbles are there. If it has 90 marbles and 1/3 of green, 1/3 of 90 is equal to 30. So there must be 30 green marbles. So then the ratio of green marbles to the total number of marbles is 30 green to 90 total. And again, this is a part to whole relationship because green marbles is a part and 90 marbles is the whole. What about the ratio of non-green marbles to total? Well, if there's 30 green marbles and there's 90 marbles total, then there's 60 non-green marbles. So that's going to be 60 to 90. Again, this is part to whole. What about ratio of green to non-green? Well, if there's 60 non-green marbles and 30 green marbles, the ratio of green to non-green is 30 to 60. And this one is actually a part-to-part relationship, or a part-to-part ratio, because both of these are parts, and we're comparing two parts. Let's look at solving word problems with proportions. So just a recap of proportions, when we know a ratio and you want to apply it to a different scenario, like in the case of the paint where we knew the ratio of red to white paint, which was 2 to 5, but we wanted to apply that to what if we had more red paint, then how much white paint should we use? That's what it means by when we're applying it to a different scenario. So anyway, when we know a ratio and we want it to apply it to a different scenario, we can use proportions to set up equivalent ratios and calculate the unknown quantities. So for example, a garden needs 1 gallon of fertilizer for every 4 square feet of soil. How much fertilizer is needed for 24 square feet of soil? So again, we know the ratio for we know that it's 1 gallon for every 4 square feet of soil. But what if we had 20 square feet instead? How would we solve this? In the previous example, we just use an equivalent fraction. And although we could do that here too, I want to show a different way of solving it. We could also cross multiply. So if you multiply 1 gallon times 20 square feet equals 4 square feet times x gallons, that's going to be 1 times 20 is 20 equals 4 times x. And you divide both sides by 4 and you'll get x is equal to 5. So that's going to be 5 gallons for 20 square feet. That's another way that you could solve a proportion. There's more than one way to set up a proportion, but for it to be correct, you need to make sure that you have the same units. You need to make sure that the same units are aligned in your proportion. So either keep the same units on the same side of the equation or keep the same units on the same side of the divisor line. So let's go back to this example for a second. Actually, let me not erase this. Let me keep this here. So remember, we said either keep the same units on the same side of the equation or the same side of the divisor line. So in this case, notice how we keep the number of gallons on the same side of the divisor line. In this case, both of the gallons are on the numerator and both of the square feet units are on the denominator. We could also set it up so that we have 4 square feet over 1 gallon equals x, or 20 square feet over x gallons. This is also correct because notice how again the units are on the same side. In this case, both the gallons are on the denominators and both of the square feet are on the numerators. So that's also correct. The third way that you could have it is if you go back here, keep the same units on the same side of the equation. So what if we had 1 gallon over x gallons equals 4 square feet over 20 square feet. This is also correct. Notice how the square feet are on the right side and the gallons are on the left side. So we have the same units on the same side of the equation. This is also correct. All three of these ways are correct. Now let's look at something that would be incorrect. Let's say that I did 1 gallon over 1 gallon over 4 square feet equals 20 square feet over x gallons. This would be incorrect because we're not satisfying any of our rules. We either need to make it so that units are on the same side of the equation or on the same side of the divisor line. But in this case, we're not satisfying the rule about being on the same side of the equation. We have gallon and square feet on one side, gallon and square feet on the other side, and we're also not satisfying the rule about being on the same side of the divisor line. So we have gallon on top and square feet on top, gallon on bottom and square feet on bottom. So that's not going to work. This is an incorrect proportion, and we would get an incorrect answer if we tried to solve it. So keep that in mind when you're setting up proportions. Either same side of the equation or same side of the divisor line. Now let's take a look at unit rates. So first, let's look at converting between units. We use units like seconds, kilograms, and meters to measure time, mass, and distance, but there are often multiple ways to measure the same quantity. For instance, inches, feet, and kilometers all measure length, they just use different scales. Unit conversion is a process of expressing a measurement in different units without changing the actual value. So if I say that 12 inches is equal to 1 foot, the actual value, the actual length is the same. I'm just using different units. Let's look at an example. A standard guitar is typically 39 inches long. How long is that in centimeters? So we have 39 inches, and what I'm going to do here is multiply this by 2.54 centimeters over 1 inch. And notice what happens. I have 39 inches over 1. What's going to happen is that the inches on the top and bottom cancel out, and I'm just left with 39 times 2.54 centimeters. And my units are now in centimeters. So if I do that math, that's going to be 99.06 centimeters. That's how I can convert from inches to centimeters. One thing to keep in mind is that, let me keep that there actually. One thing to keep in mind is that we couldn't do something like this. This would be incorrect. 39 inches over 1 equals, times 1 inch over 2.54 centimeters. This would be incorrect because notice how our inches are not canceling out now. We're multiplying inches times inches. We would end up with 39 inches squared over 2.54 centimeters. That's not getting us where we want. We're not canceling out the inches unit. Instead, we're squaring it. So this would be incorrect. You want to multiply it like this. Okay, how to convert between units, the ratio approach. So when you're told something like 1 yard is equal to 3 feet, you can treat it as a conversion ratio. So 1 yard over 3 feet, or 3 feet over 1 yard. This is kind of like what we were doing with the inches and centimeters. So the way that this would work is you multiply your original measurement by one of these ratios depending on which ratio you want to cancel, which is what we just did with the inches. So let's look at an example. Convert 3,500 grams into kilograms. Use 1 kilogram equals 1,000 grams. So we have 3,500 grams over 1, and I'm going to multiply this by, I'm going to put 1 kilogram on top, and I'm going to put 1,000 grams on the bottom. That way the grams cancel out, and I'm left with 3,500 times 1, or 3,500 kilograms, and I'm done. Again, if I put grams on top, that would give me grams squared, and that would be incorrect. Multi-step conversions. Sometimes you need to chain multiple conversions together. So for example, yards to inches. If we want to convert 2 yards into inches, we need to first convert yards to feet. So we would do 2 yards times 3 feet times 3 feet over 1 yard. And this is going to cancel out the yards and give us 6 feet. Then we're going to convert 6 feet into inches using 1 foot equals 12 inches. So 6 feet over 1 times 12 inches over 1 foot. And again, feet are going to cancel, and I'm left with 6 times 12, or 72 inches. converting units within rates. So given a rate, we want to find the quantity per 1 unit of time. This is called a unit rate. For example, if a train travels 400 miles in 5 hours, how many miles does it travel in 1 hour? So I'm going to set up a proportion here actually. I have 400 miles in 5 hours. I want to know, again, I have this rate, I have this ratio. I want to apply this to a different scenario. What if it was 1 hour? And notice how in this scenario, my denominator is 1 hour. So unit rate is actually just a special proportion or a special rate where the denominator is equal to 1. This is not a unit rate because the denominator is equal to 5. We want to find the unit rate where the denominator is equal to 1. And we can use a proportion to achieve that. So I can honestly just use equivalent fractions. I divide by 5 here. So I should divide by 5 here. 400 divided by 5 is going to be 80. So this should be 80 miles. 80 miles per 1 hour. This is a unit rate. Okay, now let's talk about percentages. A percentage is a ratio out of 100 that represents a part to whole relationship. Percent literally means parts per 100. So remember that percent is just a ratio. It's the same thing as a ratio, except it's a special ratio where it's out of 100. Percentages are used in everyday situations like discounts, test scores, population data, and more. Being fluent with percentages helps you interpret data, solve problems quickly, and understand real-world situations better. So, to calculate percentages, we use this formula. Part over whole times 100. So let's look at an example. You answered 36 questions correctly out of 40 on a test. What percentage did you get correct? And actually, let me go back here. Let me do this. Percent equals part over whole times 100. So if we take this formula and we apply it to this situation, the part is 36. That's how many questions you got right. And the whole is 40. So 36 over 40. Notice how this is a ratio, right? This is a part. This is a whole. This is a part to whole ratio. So we're going to take that times 100. And that's going to be our percent. So 36 divided by 40 is 0.9 times 100 is equal to 90%. So you got a 90% on that test. Let's look at another example. This one says, what is 160% of 25? Now this may seem a little weird because the percent is greater than 100. That just means that in this case, the part is bigger than the whole. Now what does that actually mean? That's like saying that we're taking, remember that one whole is 100%. One whole is 100%. We have 160%. So it's like saying we have one whole plus 60% more. So before we get back to this one, let's look at another example. Let's say that I wanted to know what is 160% of a chocolate bar. That's like saying, if I can draw this correctly, that's like saying we're going to take this entire chocolate bar plus another 60%. So we have the whole plus more. That's what 160% is. Now if we get back to this one, the percent is equal to part over whole times 100. Well, we're given the percent. So let's put in 160% on the left side. And the whole is 25. So we can put that there. So what we're solving for is the part. I'll call that x. So what I'm going to do to solve this equation is, first, I'm going to divide both sides by 100 to get rid of that. And I end up with 1.6 is equal to x over 25. Then I'm going to multiply both sides by 25. And I'll end up with x is equal to 40. So 40 is 160% of 25. And notice how 40 is one whole within 40. We can split up 40. We could write it as 25 plus 15. So that's one whole 25 plus 60% of 25. That's what that means. Since 100% represents a whole, if we know 1 percentage, then we can subtract to find the other. So let's look at what that means. If a school cafeteria sells only fruit juice and milk, 68% of the drinks sold are fruit juice, then what percentage are milk? Well, we know that the whole is 100%. We know that 68% are fruit juice, and the rest must be milk. So what we can do is take the entire whole and subtract 68%, and we end up with 32%. So therefore 32% of the drinks are milk. Now we're asked, if they sold 250 drinks, how many were milk? Well, we know from this previous part that 32% are milk. So we need to find 32% of 250. There's a couple ways that we can think about this. One way is, you may or may not know, but when you see the word of in a math equation, it means to multiply. So when you see 32% of 250, that's like saying 32% times 250. If you convert 32% to a decimal, that's 0.32 times 250. So if you plug that into the calculator, that's going to be 80. So 80 drinks were milk. Another way that we could think about it is, remember that percent is equal to part over whole times 100. In this case, the whole is 250 and the percent we know is 32. So 32 is equal to part. So X here is the amount of drinks that were milk. And the whole, again, is 250 times 100. Again, first we divide both sides by 100 to get rid of this, and we end up with 0.32 equals X over 250. Then we multiply both sides by 250, and we get X is equal to 80 again. So either way, we get 80. If you're given a percent and a part, then you can work backward to find the whole. Let's look at what that means. For example, there was a survey about a new community park. 72 people said that they liked the new community park, and that was 45% of all respondents. How many people were surveyed in total? So we know that, they surveyed some amount of people. Let's call it X amount of people. And 45% of X is equal to 72 people. So we want to find the whole. Now here's how we can solve this. We're going to set up a proportion. We're going to do 72, which is a part of, the respondents that said that they liked the new community park, over X, which is the whole. And we're going to set that equal to 45%, right? Because 72 is equal to 45%. Over 100%, because the whole must be 100%. Now we can cross multiply, so I'm going to do 72 times 100 equals 45x, and I get 7200 is equal to 45x. Now I'll divide both sides by 45, and I get that x is equal to 160. So there was 160 total respondents. Percentages can be written in several different ways. So for example, we have 10%. There's multiple ways that we could write this. One way obviously is 10%. Remember also that percentages are just ratios out of 100. So I could say that this is also 10 over 100. Or I could say that this is 0.10. If I do 10 divided by 100, that's equal to 0.10. If we look at another example, I could say, what about 160%? Well, that's equal to 160 over 100, or 1.6. So both of these, or all three of these, are the same thing. Remember that percentages can be written as either a percent, a fraction, or a decimal. And if it's written as a fraction, it's always going to be out of 100. Translating word problems. So to convert word problems into percent equations, you can use this key. So what is referring to the variable x, is means equals, of means multiply, we looked at that part before, and percent is divide by 100. We also looked at that part before. When calculating a percent change from an initial to final value, find the difference between the values, divide the difference between the initial value, and convert the decimal to a percentage by multiplying the quotient by 100. And we'll look at examples of this when we look at SAT problems. Now let's talk about distributions. So to summarize a dataset, we often use a few key statistics that describe the center, spread, and shape of it. These help us quickly identify what's typical in the data and how the values vary and how the data is distributed overall. The center of a dataset gives us a sense of what the typical value looks like. On the SAT, the main measures of center are the mean, which is the average of the values, the median, which is a middle value when the numbers are arranged in order, and the mode, the value that occurs the most often. The mean is calculated by adding up all the values and then dividing by how many values there are. So the sum of all values divided by the number of values. And that's just like calculating the average. The mean is equal to the average. The median, so to find that, we're going to sort the numbers from smallest to largest and then find the middle value. If there's an odd number of values, then it's going to be the middle number. But if it's an even number of values, we're going to find the average of the two middle numbers. So let's look at what that means. Let's say that we have this 1, 2, 3, 4, 5. This is sorted in order, so we would go and find the middle value. If I cross out one by one, I get that the middle value is 3. So then that's my median. That's with an odd number of values, but what if there was an even number of values? So let's say 1, 2, 3, 4. In this case, I have two values in the middle, 2 and 3. So what I would do is find the average of those, 2 plus 3 over 2, which is equal to 2.5. So then that would be my median. The mode is a number that occurs the most frequently. A dataset can have no mode, one mode, or more than one mode. Let's look at an example. Actually, before we do that, let's look at what the range is. So the range is just the difference between the largest value and the smallest value in a dataset. So now let's look at an example. Find the mean, median, mode, and range of the test scores. So what I'm going to do first is I'm going to sort these test scores in order from least to greatest. So I have 70. Then I have, before 70, I have 60. Then I have 70. Then I have 75. Then I have 85. Then I have 90, 95, and 100. Okay, so let's start with the mean. So what I'm going to do is first notice how there's 1, 2, 3, 4, 5, 6, 7 values. So I'm going to add up all these values, 60 plus 70 plus 75 plus 85 plus 90 plus 95 plus 100. I'm going to add up all these values and I'm going to divide by 7 since that's the number of values that we have. So let me put this into the calculator. And we get that the mean or the average is approximately 82.14. So that's the average score. Now let's look at the median. So again, for the median, we're just gonna go and find the middle value. So I'm gonna cross out the values from the ends one by one until I get to the middle value. In this case, since we have an odd number of values, it's just going to be this middle value, which is 85. So that's the median. This is the mean. Okay, and now the mode. So remember that the mode is a value that occurs most frequently. So let's see, we have 60, 70, 75, 85, 90, 95, 100. So in this case, there's actually going to be no mode because all the values occur exactly once. No value occurs more than other values, so there is no mode. Although if, let's say, two students scored 100, let's say that there is actually another student that scored 100, then 100 would be the mode because that would occur the most times. But in this case, there's going to be no mode because all values occur one time. And lastly, the range, which remember, that's the largest value minus the smallest value. So 100 minus 60 is 40. And so that's the range. Okay. Now let's talk about standard deviation. While you don't need to calculate standard deviation on the SAT, you do need to understand what it means. It measures how far the values are on average from the mean. So a small standard deviation means that the data is going to be clustered closely around the mean, and a large standard deviation means that the data is more spread out. Let's say that the mean is 5 and my standard deviation is 10. That would mean that my average value is 5 and all the other values on average are 10 away from 5. So they're pretty spread out, right? Versus, let's say that my standard deviation instead was 2. That would mean that on average, my values in the data set are 2 away from 5 or from my mean. So there's a smaller spread. Now let's look at an example of that. It says, if John and Ben both jogged an average of 45 minutes per day, which one has a larger standard deviation? So if you look at their jogging times each day, if you were to find the average of John and the average of Ben, they would both be 45. They both have the same average. But if you look at John's jogging time, he's more consistent, right? 30 minutes, 45, 30, 45, 45, 60. So in general, he's pretty close to his average time of 45 minutes. So he has a pretty small standard deviation, a small spread, because his values are not that different from the mean. If you look at like the difference between the mean, which is 45, and John's jogging time, right? Over here, the difference is 45 minus 30, which is 15. Over here, it's 45 minus 45, which is 0. The distance between 45 and 30 over here is 15. If we keep going, you can see that the average, distances is pretty small, right? So the standard deviation is not that much. Versus Ben, he's more inconsistent with his jogging time. One day he does 30 minutes, next day he does nothing. Next day he does 120 or 90. Other days he does nothing, right? So his values are much more spread out. And if we were to find the difference between, his values and the standard deviation, his values and the mean, it would be, 15 today, 45 tomorrow, then 0, then 15, then 45, then, this would be 75, I think. So his values vary wildly, so he has a higher standard deviation than John. Now let's talk about what an outlier is. An outlier is a value that's far away from the rest of the data. Outliers have a big effect on summary statistics. So the effect on the mean and the spread is that outliers will pull the mean toward them and they'll increase the range and standard deviation. They won't have they won't have as much of an effect on the median or the mode because they're more stable and they're not going to change much unless the outlier's in the middle. It's not going to affect the median and it probably won't affect the mode at all. But it is going to pull the mean toward it and it's going to increase the range and standard deviation. Let's look at an example. Let's say that I have a pretty normal data set. Let's say my data set is 2, 3, 4, 4, 4, 5, 6, 7. Okay. And let me add one more, 7. Okay. So let's calculate the statistics for this. We have that the range is largest minus smallest, which is 7 minus 2 or 5. The median is the middle value. So if we cross out the values until we get to the middle, that's going to be 4 is the median. the mode is going to be 4 because you can see that 4 occurs 3 times. The next largest frequency is 7, which occurs twice, but since 4 occurs the most times, 4 is going to be the mode. And lastly, the mean. Okay, let's calculate the mean, and what we're going to do to do that is just 2 plus 3 plus 4 plus 4 plus 4 plus 5 plus 6 plus 7 plus 7. Okay, so we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So I'm going to divide this by 9. And let's do that math. That's going to be equal to 42 over 9, which is 4.66. So our mean is 4.66. So this is a pretty standard data set, right? Now let's say that I add an outlier. So I'm going to add 100 to this data set. Notice how it's, way different from the other values. It's way larger, right? So that's what an outlier is. It's, way different or like much larger than the other values. Now, I'm giving an extreme example here just to illustrate the point, but in reality, outliers usually are not this extreme. A more realistic outlier would be like 30. That's a more realistic outlier. I'm not going to use that in this case just because I want to use like a really large number to illustrate the point, but keep in mind that outliers are usually not this different. They would usually be, maybe like around 20 or 30 for this data set. Still like different and larger or smaller, but not, that much of a gap. Anyway, if we recalculate our values, our range is now going to be 100 minus 2, right? Largest minus smallest, so it's 98. Notice how our range changed a lot. Again, that's mainly because I chose like a really large outlier, but the range is going to change based on if you have an outlier or not. The median, let's see. Again, I'm going to go one by one and find the middle value. And we can see that it comes down to between 4 and 5. So I'm going to find the average of those, which is 4.5. So my new median is going to be 4.5. You can see that it's not that different from before. It didn't change that much. The mode is actually still going to be 4 because, again, the most repeated value is still 4, so that's not going to change. The mean, I'm going to follow the same steps to calculate the mean, except over here, I'm going to do plus 100, and instead of dividing by 9, I'm going to divide by 10 now, since that's how many values I have. So that's going to be 142 over 10, which is 14.2. So now notice how the mean went all the way up to 14.2. It went way higher, and notice how the mean was pulled in the direction of the outlier. So if the outlier was instead, like if it was like negative 20, right? Then the mean would be pulled in the negative direction instead of the positive direction. But since my outlier is a large positive number, the mean is going to be pulled in that direction. If you know the average of a data set, but one value is missing, you can work backwards to find it. The way that you can do that is you're going to multiply the mean by the number of values to get to the total, and then you'll subtract the known values from that total. So let's look at an example to see what that means. We're given 5 numbers here, and we're told that the mean of these numbers is 30, but we're missing one of the numbers, and we want to find that number. So what we can do is we can say, remember that the mean is equal to adding all the numbers divided by the total number of numbers, and there are 5. So we know that the mean, we're given that it's 30. So we can plug that in here. And now we can work backwards to solve it. So first I'm going to multiply both sides by 5 to cancel out this 5. And I'll end up with 150 equals, and then if I add these numbers, 20 plus 20 plus 40 plus 60 is going to be 140. So 150 equals 140 plus x. Now I can just subtract both sides by 140, and I get x is equal to 10. Alright, now let's take a look at data representations. So a scatter plot is a visual way to show the relationship between two variables using points in the coordinate plane. Each point represents a pair of values, one for each variable. Usually the horizontal axis or the x-axis shows the independent variable and the vertical axis shows the dependent variable. So when we're describing a scatter plot, we consider the direction. So does the data trend upward, which is called a positive correlation, or downward, which is a negative correlation? And is the form, so is the relationship of the data linear, like a straight line, or does it curve? And also, is the data strong or weak in its correlation? Now, usually on the SAT, for as far as form goes, it's only going to be linear. You're not going to have to worry about, any other type of form of data. So just focus on linear for scatter plots at least. So let's look at an example. So first we're going to consider direction. So does it trend upward or downward? That's pretty self-explanatory. So let's say that we have an axis and we have a scatter plot that looks like this. This is trending upward. So the direction would be upward or positive. Versus this, which would be negative. Notice how this one is going up in general, this one is going down. Okay, now the form. So is it linear or does it curve? So linear generally looks like these two. Both of these relationships are linear. Notice how they can be modeled using a line. There's also, other types of forms. So for example, something like this would be logarithmic. And there's, exponential and other forms. But as far as scatter plots go, you're only going to have to worry about linear on the SAT. Then we have strength. So are the points tightly clustered along a line or more scattered and weak? So if you look at this one we would say is a strong positive correlation. This one is a strong negative correlation. Versus something like this. We could say that this is more of a weak positive correlation. Notice how, let me change this a little. Notice how the points are a little bit more scattered. They're not as tightly clustered, although they do still have a general positive trend. So this right here is a weak positive correlation versus this, we could say is a weak negative correlation, because although there is a general trend of it going down, the trend is pretty weak. So that's a weak negative correlation. And again, this one here, strong positive, this one strong negative. Okay. The line of best fit is going to represent the overall pattern of the data. And although not every point lies on this line, the line is going to give us a general sense for how the variables are related. For any data point, the difference between its actual y value and the y value predicted by the line of best fit is called a residual. On the SAT, you may be asked to compute this difference. So the line of best fit, the purpose is not to touch as many data points as possible. The purpose is to get as close to as many data points as possible. So let's say I have a scatter plot like this. And I draw a line of best fit, something like this. Notice how it's not touching that many data points. It's touching like one data point. But the point is that it's going to minimize the difference, or it's going to get as close as it can to, in general, to all the data points. Also, the residual is going to be the difference between the actual y value and the predicted y value. So any point on this line of best fit is predicted, right? The actual values are the dots, on the scatter plot. So let's say that we're talking about this value, right? This here is the actual value versus down here is the predicted value on the trend line or on the line of best fit. So the difference between the actual value and the predicted value, which is, this distance, that's called the residual. All right. You can interpret the slope and y-intercept of the line of best fit in context. So the slope shows the rate of change or how much the dependent variable increases or decreases for each unit increase in the independent variable. And the y-intercept shows the starting value when the independent variable is 0. This is basically just like how it is with regular linear graphs. So that's the same thing as that. So for example, a scatter plot which is not shown displays the number of weekly practice hours and test scores for a group of students. The line of best fit has the equation y is equal to 4.5x plus 60. So we would say that the slope or a 4.5 means that for every additional hour spent practicing, the test score increases by about 4.5 points. Or, for every value that x increases by, and remember x represents the number of hours studied, right? So every time the number of hours studied goes up by 1, the score increases on average by 4.5. And the y-intercept of 60 means that a student who doesn't study at all is predicted to have a score of 60. Let's look at another example. Suppose a student practiced for 6 hours. What is the predicted score? If he actually scored an 88, what is the residual? So our equation is y is equal to 4.5x plus 60. If the student studied for 6 hours, then we can plug in 6 for x and we get y is equal to 4.5. And also I'm gonna put this as y hat because that's what we use to represent the predicted value. So y hat is equal to 4.5 times 6 plus 60. And don't worry about the y hat, it's just meant to represent that this is predicted and not the actual y value. So if we simplify that, let's see, that's going to be 87. So the predicted score for the student is 87. Now, he didn't actually score an 87, he actually scored an 88. So the residual is going to be the difference between his actual score and the predicted score. So that's going to be a residual of 1. So when you're using a line of best fit, use the equation to predict values, not individual points. If you're predicting a value within the range of your data, then your prediction is more reliable. But if you're predicting the value outside of your range, then you're making an extrapolation, which is less accurate. So, maybe you have a range of values like this, and you have this line of best fit, right? If you're predicting values, within this x range, then your prediction is going to be more accurate, right? But if you're predicting, let me extend this axis a little more. If you're predicting an x value like here, let's say that we predict that the x value here is going to be, somewhere like this. This is a predicted value. This is not going to be as accurate because we don't really have that much data around this blue point that we can make a good prediction for. So this is not going to be that accurate. Versus these values, if we predict a value closer to here, that's going to be more accurate.